So one thing you could do is you could memorize the pattern. This is the x2 plus ay pattern. x2 plus ay gives us the y2 plus ax. And so you memorize this. This is the alternate single replacement form for this, or use the chart method. So memorize this. This is wrong, by the way. Or use chart method. This one you have to use the chart method. When you're dealing with oxidizing gases, there's no other way of doing it. Here you can memorize an alternate pattern, or just use the chart method. The reason is because potassium ion, the chart method says the potassium ion is the oxidizer, right? That's okay, potassium ions are oxidizers. Bromide ion is not an oxidizer. So potassium ions are an oxidizer. And so, but we have a problem because chlorine, is chlorine a reducer? A is supposed to be the reducer, but is chlorine a reducer? The answer is no. Chlorine's not a reducer. What is it? It happens to be one of the more powerful oxidizers in the chart. And so single replacement totally misassigns this. It turns out that chlorine is the most powerful oxidizer, and bromide would be the most powerful reducer in this mixture. We'd have to use the chart method for this, or use the alternate form of single replacement. C is water. Single replacement does not factor in water as a reactant. And so that's a problem. For example, here. Let's use sodium metal plus KCl. What do you predict for this? Yeah, what we predict would be sodium chloride and potassium metal. Okay, then we look at the activity series. You know, sodium versus potassium. Which one's more active? When we look at the activity series, it turns out which one's more active. Lithium's the most active. Lithium, and then number 2 is potassium. Sodium's number 4 on the list. So in this case, what we're doing is we're going from less active to more active. If we're going from less active to more active, then is there a driving force? No. No driving force. So single replacement predicts no reaction. But you'd be in big trouble if you did this. You'd be in big trouble because you're going to get an explosion. Why? Because potassium ions aren't the strongest oxidizer around in this mixture. Do you know what the strongest oxidizer in this mixture is? Water. Now, water is kind of tricky on our list. Where does water fit in? Isn't water at the bottom of the list? Did I just screw up my slide? I just screwed up my slide. Yeah. It doesn't matter. Isn't water the worst oxidizer on the list? No, where does water fit in? The worst oxidizer on the list is what? Is Li+. Its hydrogen is not the worst. Even though it's 0, It's 0 just refers to sea level. You know, can you go lower than sea level? Yeah. And therefore, we can go worse than hydrogen. What's worse than hydrogen? Lithium ion. Lithium ion is the worst oxidizer on this chart. If lithium ion is the worst, where does water fit in? Between zinc and aluminum. And so it turns out if water fits in between zinc and aluminum, then water is a better oxidizer than potassium. So this was the wrong reaction. The reaction is not between sodium and potassium ions. The reaction is between sodium and water. And what happens when you mix sodium metal with water? Explodes. So it's big trouble. So this is why, in a case like this, we got to use the chart method. This is wrong. Now, if we don't have one of these scenarios, then the chart method works nicely. Looks good. I mean, not chart method, a single replacement method works nicely. Okay. So you ready to try one? Yeah. Why don't you do this one?